Okay, thank you for the kind introduction, and also thank you for inviting me here. It's my pleasure to give a talk here. So today I'm going to clarify what this question means, and also we'll try to answer this question. And this work is collaborated with my former colleague at Princeton, including Stephen in the audience. So I heard that most of the audience are not cosmologists, so I will first explain what's the standard practice in the cosmological data analysis. And then I will introduce a new kind of technique to optimally extract information in the cosmological data, which is known as field level inference. And finally, I will compare this new kind of optimal method with a conventional standard method to say something or to answer the question in the title. Okay, so let me start from the standard stuff. So here I will explain the basic framework of the cosmology. So in the very broad picture. So ultimately, what we cosmologists can do are summarize two stuffs. So given some cosmological model, which is parameterized by some parameter theta, first of all, we can we'd like to predict something about the initial conditions. But the point here is we cannot predict the kind of realization of the initial condition. Rather, we can just predict its statistics. I mean, we cannot predict where's overdense or where's underdense in the universe. Rather, we can just specify their statistical property. But then, given some realization of initial condition which satisfies some statistics, we can, in principle, compute the subsequent evolution in a deterministic way to get the final observables. And here I'm showing some schematic picture of this process. So we first specify some model, cosmological parameter. Then what we can do is just compute some spectrum or some, in general, some PDF of the initial conditions, which depends on this cosmological parameter. Then, based on these statistics, we can generalize some random field. And given this random field, we can, for example, run some n-body simulations to get a final large-scale structure. And what we'd like to do in the end is to compare this theoretical prediction with some real data to get cosmological information or cosmological parameter constraint. So this is what we'd like to do. And formally, this can be more, we can kind of write down some equations for that. I would like to say this cosmology inference is well-defined hierarchical Bayesian problem. What I mean is, again, first we specify some cosmology or cosmological parameter. Then we cannot predict this map. What we can do is just some, for example, say, power spectrum. And in the standard inflationary model, which is kind of leading early universe model, the standard inflationary model predicts this random field should look Gaussian. So in this case, the statistical property of the random Gaussian field is completely specify their power spectrum or two-point function, and we can kind of predict what the kind of this power spectrum looks like. And this is the kind of job for early universe cosmologist. And given some statistical property, we can again generalize, for example, random Gaussian field here. And in the Bayesian language, this is a kind of prior knowledge about the initial condition. Then, given again the realization of the initial condition, we can compute or we can simulate the subsequent evolution to get some observables like this. And in comparison, we also have to use some statistical language which is called likelihood. And this likelihood is kind of conditional probability of the data given the model. I mean, how likely the data is given some theoretical prediction. And again, I'd like to remind you, this prior is kind of conditional probability of the initial condition given some cosmological model. And for this part, if you assume standard stuff, I mean standard inflationary model, we can write down the kind of analytic expression for that, as I said. This is just a Gaussian random field with some power spectrum. But for this part, likelihood, in general, kind of it's quite hard to write down some form. But forgetting about this kind of technical details, formally, we can write down our final target, which is a posterior distribution of the cosmological parameter given the data. Now, according to the Bayes theorem, this is just written as a product of this likelihood times prior. And the resultant posterior is a kind of joint probability of the cosmological parameter and the realization of the initial condition. But this is a problem. I mean, what we ultimately would like to know is the posterior distribution of theta, not this guy, this realization of the initial conditions. So the problem here is we cannot predict, again, the realization of the initial condition. So we don't know what the realization behind of this data. So we have to marginalize over them. In other words, if you compare this map and this map, if you are careful enough, you can probably notice they are kind of different map. But we cannot tell that this difference comes from the wrong cosmological parameter or just a realization of the initial condition different. So in the language of the statistics, we have to marginalize over this kind of latent variable, so-called. So this is done by a so-called ensemble average. So in the cosmology textbook, you'd encounter many this average, average symbol. This is called ensemble average, and this is nothing but the marginalization of the unknown initial condition. So what this symbol means is, as I said, we can specify some statistics and generate many realization of the initial condition that satisfy these statistics and evolve them into the final intensity field, but we kind of average over them to get some quantity. Mathematically, this is just integral over all the possible configuration of the initial condition with some weight. The weight is given by the prior of the initial condition, again, which is Gaussian. We know its form. So in a standard practice, what we can do is to take this average or marginalization before comparing the theoretical prediction with the data. I mean, we can take this ensemble average at this level to get some quantity or to predict some quantity. So this requires you to specify some quantity, which is called summary statistic. And for example, I assume you know at least name the power spectrum. So power spectrum, the ensemble average of the power spectrum is written as just you can insert some two field here and multiplying some weight, which is again nothing but the prior of the initial condition, and take and do the integral to get this average. And okay, let me. And theoretical prediction for the power spectrum or any other statistics is made in terms of this ensemble average. I mean, in the textbook and reviews, you encounter this kind of symbol. In any case, you have to compute this kind of statistical average quantity in the theoretical side. And on the data side, we have to mimic this quantity. And to do that, we usually assume and usually approximate this ensemble average by some statistical average. And for example, focusing on the power spectrum case and kind of simplified setup, we can just construct some estimator for the power spectrum, some density squared in the some k beam. And what we're doing is, so here on the map level, we have millions or billions of data dimension. But doing this marginalization of the initial condition, we are compressing the full data set or full kind of theoretical prediction into just a number of, just a few numbers, not a few, but order of 10 numbers. So here's a kind of example for that. So this is showing the power spectrum measurement from the both. X-axis is a kind of scale, and the y-axis is the amplitude of this power spectrum. And each dot here corresponds to the measurement from the data. And this solid curves are corresponding to the theoretical prediction after taking over the average. We'd like to compare this solid curve and this point to infer some cosmological parameters. So in short, so here's a kind of simplified flowchart of the task of observation cosmology. So in the standard method, first you have to specify or you have to choose your favorite summary statistics. And usually people take a 2-point function, the power spectrum. But you can choose whatever you want here. In any case, then you have to measure that summary statistics from the data. This involves to construct an unbiased estimator, blah, blah, blah. And this requires some other work, but in any case, you have to do it. At the same time, you have to develop some theoretical prediction for that summary statistics, this solid curve. And for this, you can use perturbation theory, as Stephen explained in yesterday's seminar, or n-body simulations. And having this theoretical prediction and some measured quantity of the summary statistics on the hand, now we can compare them by using some likelihood. And I won't go into details, but usually people assume some Gaussian functional forms for the likelihood. And using this analytical form for the likelihood combined with some prior of the cosmological parameter, we can just run some MCMC to infer cosmological parameter. So here's a very summarized flowchart. We have some data, but we have to again marginalize over the initial condition, or we have to compress the full data into a set of summary statistics. And after that, we can compare this solid curve and the point to get final constraint on cosmological parameter. This is what people usually do in cosmology. So, okay. So far, does anyone have any questions? If not, I can move on to the kind of new method, or kind of optimal method. So, okay. Actually, this paradigm, the standard practice in cosmology, has been successful in the last 10 or 20 years. But there's some, not problem, but not kind of issues. So, as I said, you can choose whatever you want for the summary statistics to analyze the data. And one important fact in cosmology is the initial condition, initial fluctuation follows the Gaussian random field if you believe the standard inflationary model. So in this case, so for random Gaussian field, we know, or it's well known in the statistics, that the compression into the power spectrum is optimal, or in other words, power spectrum is a sufficient statistics. So you do not lose any information if you compress the data into the power spectrum. But and this is true for the CMB. But for large-scale structural galaxy survey, due to the nonlinear coupling by gravity, the resultant, the observed field is not Gaussian. So here I'm showing some simple example. On the left, I took some n-body snapshot. On the middle, I took some n-body snapshot here, and I measure their power spectrum, which is shown by, I think, blue here. And using this measured power spectrum and using the initial random seed to generate this n-body simulation, I generated some random Gaussian field. And by construction, they share the same power spectrum. So if you only use the power spectrum, you cannot distinguish between them. But clearly, they are different. So to quantify this difference, recent years, many people are proposing many kind of summary statistics. So some people are arguing Minkowski functional, people should use Minkowski functional, whatever. This is just a random list of the proposed summary statistics to analyze cosmological data. But the real question, kind of what we ultimately would like to know is what is the optimal summary statistics to analyze the galaxy density field. And actually, in cosmology, there is some way to analyze the data in an optimal way, which is known as the field level inference. So in the following, I would like to quantify what is so this if this difference has additional cosmological information or not. So field level inference is also have to do the marginalization over the initial condition, but in kind of different way. So in the previous case, we take ensemble average before comparing the data. But in the field level inference, or so-called, the so-called field level inference, it's trying to marginalize over the initial condition while comparing the theoretical prediction and the data. And which means we write down some likelihood between this map and this map. So, I mean, we have to have some theoretical prediction at the map level or field level, and compare each voxels or each Fourier mode to get some cosmological constraint. So we are comparing this map and this map in each, it's hard to see, but each voxels or each Fourier mode. And this means we have to evaluate this high dimensional integral in a numerical way. In the previous case, we just take we can just compute this integration by pen and paper. But if you'd like to do this explicit marginalization, then you have to evaluate this integral on the computer. And this is a big challenge because the dimension of this integral is, well, in principle, the dimensional or measure of this integral is infinite. But of course, on the computer, we discretize the field. But even after discretization, the dimension of this integral or dimension of the initial condition is quite high. It's kind of order millions or billions. So you have to compute millions or billions of dimensions of integral, which is super challenging stuff. But now it's kind of doable stuff. I will skip all the details that enables this computation, or machinery. But the point is we can do it now. And seeing is believing. Here I'm showing some demo movie. Sorry, it's already started. So what I'm doing here is first sample some cosmological parameter, then compute the linear power spectrum, generalize some random Gaussian field based on this, and evolve them into the final density field, and compare some mock data at the field level or map level, and evaluate the likelihood, and repeat this to get converged. And this map is kind of initial guess. And of course, this is wrong. I mean, wrong means this doesn't look like this, and this doesn't look, okay. So this bottom line is a kind of truth or input. They are kind of different. And also, this is a kind of contour or parameter space for some cosmological parameter, and this is a truth, and this is fast guess. Of course, this is wrong. But repeating these evaluations, they are trying to find a true underlying latent variable as well as a cosmological parameter by evaluating this likelihood at the field level. And here I'm showing kind of minus log posterior. At initial stage, it has some quite high value, but in the warm-up phase, it's getting decreased and converges to some value. So this is what we are doing in the kind of cosmological field level inference. And the point is here, we do not compress the data. We are using all the data available at the field level. So by definition, this should be a kind of optimal way to analyze the data. So, okay, so.
When you say we, so you want elucid, or what do you mean by we?
Me.
You want your own code?
Huh?
Your own gradient, HMC,
yeah.
HMC.
Right. Right. On the behind, I'm using HMC and the gradient-based method. I mean, all the forward model is written as a differentiable way, and we can use the HMC to evaluate this.
And you propagate gradients.
Right. Exactly.
And you did your own implementation.
Well, I implemented this and also applied some mock data.
Okay, so again,
Sorry?
all these people you mentioned up there, they have various implementations of these, get
Right?
information.
Right?
So you say, are you using one of theirs or
Yeah.
you
Oh, I by myself developed this. I mean, in the previous work, I mean, I think as far as I know, this previous literature was working on the CPU and quite low dimensional stuff. I mean, the dimension of the initial condition is like 64 cubed or something like that. But here, I developed some new code, a JAX-based code, and which can run on the GPU in a quite faster way. And I can run, for example, 256 cubed initial condition or whatever. Anyway, we have our own code. And it's, of course, from my opinion, it's much better than previous code. Anyway, so any other questions so far? Okay, if not, let's move on to the main topic. So while we are working on this stuff for, I think, 2 or 3 years, there appears some controversial paper. And I heard that the first author of this paper came here and give some colloquium talk about this. And what they did is quite similar to ours. I mean, they performed the field level inference for n-body heralds and compare this field level inference result with a conventional power spectrum plus bispectrum analysis. What they claimed is even though they are working in the perturbative regime means the perturbation theory kind of works. And this kind of 0.1 or 0.12 means some wave number. And the point is, perturbation theory still works. Even though in this scale, they found a significant improvement over the P plus B if you do the field level. If this is true, we all have to work on field level. Because the improvement factor is 3 or 5. So think of the amount of budget we need to get this improvement with conventional method. But if this is true, so the natural question, of course, is where they get this additional information beyond the P plus B in the perturbative regime. So the
Can you remind us what alpha is?
sorry?
What is alpha?
Oh, alpha is kind of amplitude of in your language it's sigma 8.
Yeah.
This is the amplitude of initial conditions. But I think it's not important. I mean, the point is we can get some much tighter constraint on the cosmological parameter if you do the field level inference. That's what they do or said. So I think the problem, not problem, but the issue in their paper is they kind of jump into the quite realistic case, which is an n-body heralds, before testing all the stuff in the MOC, the more simplified toy model. So what we are trying to do in the following is to see when or why the field level inference is becoming better than the conventional method by using theoretically well under controlled example.
So sorry, quick question about this alpha. So alpha equal to 1 is the true value.
Yeah, this is kind of normalized stuff. This is just sigma 8 divided by sigma 8 input.
Well, why only if you really can reproduce the right value?
Well, I mean, this is just still 1 sigma, 2 sigma, so it's fine, I think.
So mean explains that this is because of their covariance for the P plus B. They also use very simple covariance that actually bias. So it's
Why does
Well, I will explain. If time allows, I will explain what's the kind of difference between us and them. And actually, okay.
Right. They use a simple covariance, doesn't mean the error bar
No,
is
I mean,
even wider than
no. For P plus B, they use a SBI. Actually, they didn't include a density-dependent noise in the first draft. That's a problem.
Yeah.
But anyway, that's, I think, too technical. Anyway, so what we are trying to do is kind of apple-to-apple comparison. So we have some pipeline for simulation. So we pick up some true value of cosmological parameter and run some simulator in our pipeline to generate mock data. And we added some white Gaussian noise to it to make a final mock data. And on one hand, we just run usual P plus B analysis. We measure power spectrum and bispectrum from the mock data. And we also compute the theoretical prediction in terms of ensemble average and compare them using some commonly used Gaussian likelihood to get posterior distribution of the cosmological parameter given power spectrum plus bispectrum. And on the other hand, we run the full field level inference for this mock, assuming some Gaussian likelihood. And in this case, this is correct because we added the white Gaussian noise by hand. So we kind of make the field level likelihood to be Gaussian. But anyway, so using some assumed likelihood, we run the field level to get the final posterior of the cosmological parameter given some data. And we will compare this posterior and this posterior. And another point I'd like to mention here is we use the exactly same number of Fourier mode in each analysis, which means we introduce some scale gap in the likelihood in both the P plus B and the field level, and they are the same. So this is kind of fair comparison in terms of the number of Fourier mode. Okay, so let's begin with the simplest example, which is a Gaussian random field. And as I mentioned, for Gaussian random field, we know the compression into the power spectrum is not losing any information. I mean, compression into the power spectrum should be lossless, and we should get the same result from the power spectrum analysis and the field level inference. So now we are varying some cosmological parameter and noise level. And here's the kind of result. And gray contour is obtained from the power spectrum analysis, and blue is a field level. And as you can see, they are in excellent agreement. And this is just a sanity check, but I think it's always worth checking this stuff. So this shows our pipeline is correctly working correctly as expected. Okay, then let's move on to some bit complicated scenario. And here we started to add some quadratic nonlinearity in the mock data, and which has some weird combination. But the point is, this is just some quadratic nonlinearity constructed from the linear density field. So you can just think of this as linear density field squared or something like that. Then for a moment, we fix the noise level and only focusing on the cosmological parameter and run the inference. And here's the result. And one might expect now the underlying field is non-Gaussian. So field level should be or might be better than power spectrum. But this is not the case. So what we found is even for the nonlinear or non-Gaussian random field, if you focus on the cosmological parameter, the power spectrum is still nearly optimal. They are, of course, not perfect agreement as before, as the previous Gaussian case, but the error budget looks almost the same. So one might complain, okay, this is too simplified primordial, far from the reality. But we can confirm this with a more kind of realistic case, which is a zero-bit matter density field. And this is a kind of good proxy for the nonlinear matter density field. And again, we just replace the model with some more realistic stuff and focusing on the cosmological parameters and compare the power spectrum and the field level inference. And of course, the agreement is not so good. The point is that this error budget or error bars looks almost the same. They're just 10% or 20% different. So still, power spectrum is almost optimal. So this is a bit surprising for some people, but the reason is rather simple. So now we have some nonlinearity or non-Gaussianity in the field, and actually this makes some non-zero bispectrum or any other higher order correlators. But and we can do the kind of analysis with bispectrum only stuff. And again, focusing on the power spectrum. Now here's this figure is showing the result, and this new green contour is corresponding to the bispectrum analysis. And as you can see, the constraints from the bispectrum is much weaker than the power spectrum, which is shown by gray. and which is completely overlapped the field level. And the reason behind this is the kind of signal to noise. So again, we are working in the perturbative regime. So this means this second term should be smaller than the first term. And in terms of the power spectrum and bispectrum, the leading order power spectrum should be greater than the leading order bispectrum. And if you compute a kind of signal to noise as a function of K max, or scale cut, you can get something like this. I mean, it's hard to see, but here's some line by kind of blue line. And this is a kind of cumulative signal to noise of power spectrum. And this orange curve is corresponding to the signal to noise of bispectrum. And as you can see, the signal to noise of the power spectrum is much bigger than the bispectrum, which is translated into this weaker constraint from the bispectrum. The important lesson we can learn from this kind of 2 points. I mean, the first one is the bispectrum has much smaller signal to noise. And also, if we are only focusing on the cosmological parameters, the parameter degeneracy direction between in the power spectrum and bispectrum are the same. So adding some much wider posterior, which has the same direction to the power spectrum, doesn't help.
So is there a way to understand why there is no degeneracy breaking?
Well, essentially, in the perturbation theory language, this is just a function of p linear. And this means this B has the same dependence on the cosmological parameter. Okay, this is just kind of p linear squared or something like that.
But it reflects the fact that you still consider not the general non-Gaussianity. It's by
Well, I mean, I didn't prepare that slide for that, but this is also true for zero-Dirichlet matter. If you focus on the cosmological parameter, this is the point. I mean, I will show you in the next slide where the power spectrum becomes suboptimal, of course.
Sorry, because I was actually confused with the Deldovich result. Why the power spectrum is biased, even though the
Biased?
power
It's biased?
a little bit, you know?
By just 1 sigma.
Yeah.
So I think it's just random fluctuation. This is still within 1 sigma stuff. I think it's fine. If you try another seed, then
Yeah.
yeah.
I think usually when we do like this kind of validation, 0.3 sigma is
Really? But I think 1 sigma is just a random realization.
In this case, the data, I mean, the covariance of the data, right? So you expect a 1 sigma.
Right.
uh,
Right.
When we do the validation, is we have a huge volume compared to that.
That's right.
Any other questions so far?
So that's about linear connection. So if you take into account RST, then
Okay. I will move on one by one. So this is kind of simplest case we can consider. Okay, good. But of course, we know in reality, as probably Teppei pointed out, power spectrum is not optimal statistics in many cases. And I can show you this with this simple toy model again. So what we do here is using the same model and the same analysis pipeline, but now start to vary the noise level. And here's the result. And we have a 3 contour. Gray is the power spectrum, and green the bright spectrum, and blue is the field level. Now you can see the distinct, I mean, you can see the difference between them. So the gray contour is not the same as blue. Why? Because in this case, if you look at the power spectrum only, this power spectrum consists of some signal plus noise. But if you look at the bispectrum, because we injected the white Gaussian noise, there's no kind of noise contribution to the bispectrum. So the bispectrum purely consists of some signal. So they have some different dependence on noise. So as you can see, different from the previous slide, this gray contour has different direction to this green contour. So power spectrum has different parameter dependence on this green contour. And if you compare this gray contour with this blue contour, which is field level, and this bottom line, which is showing some constraint on the noise amplitude, the improvement in the field level is mainly driven by the degeneracy breaking in this line. So this implies if I add or if I combine this P and B, then I would get the same result as field level. And actually, this is the case. So if I do the joint analysis of power spectrum and bispectrum, then I got the nearly equivalent result to the field level. So in this simple toy model, although now I started to vary the noise level, if you add the bispectrum to the power spectrum, then that's it. You don't have to work on the complicated field level stuff. But of course, this is still far from the reality. So still, I'd like to stick to this toy model, but introduce some reality here. So what I did here is introduce some so-called linear bias parameter in front of the model. So the now model is some constant times some toy model. And now, once again, I fix the noise level, but start to vary this linear bias stuff. And it's well known that if you only consider this linear term, I mean B1 times delta, then the amplitude of this delta called A is completely degenerate with B1. I mean, changing B1 is the same as changing A. So in order to break the degeneracy between B1 and A, we have to look at some nonlinear information, which is encoded in this quadratic term. So in the power spectrum language, which is kind of one loop effect. So if I compute the power spectrum from this model, I would have a linear power spectrum here, plus some correction from G2. And the point is, this term and this term have a different dependence on the amplitude. This is just 2 deltas, but this has 4 deltas. So this is proportional to A squared, but this is proportional to A to 4. But the dependence on B1 is the same. So you can break the degeneracy using this information, even if you only rely on the power spectrum. But the result is kind of nightmare, so which is shown by gray. So as I said, in principle, we can break the degeneracy, but the effect of one loop or higher order term is suppressed compared to the leading order term. So the resultant posterior has still huge degeneracy between A and B1, this direction. But if you look at the bispectrum, bispectrum has another dependence on B1 and A. And actually, this bispectrum, leading order bispectrum, is kind of greater than the one loop power spectrum. So we expect that the bispectrum has more information than this one loop power spectrum. And here, field level is again shown by blue, but we expect adding the bispectrum again recovers the field level result in this case. And again, this is the case, so it's almost invisible because they are completely overlapped. But I added some result from the joint P plus B analysis, which is shown by green. And again, this green and blue contours are totally overlapped, and they are equivalent.
I have a question, actually.
Yes. Oh my God.
No. So earlier you said that the signal to noise of P is always orders of magnitude.
Okay, that's a great point. Okay, this is total signal to noise.
Yeah.
But if you compute just a signal to noise, a one loop term with a usual covariance, then the total signal to noise, a one loop term is less than bispectrum.
So what controls what controls this comparison?
I mean, covariance are the kind of same, right?
Yeah.
But the signal is suppressed by some factor. Where is it? Right? I mean, this is just in the terms of, okay, I think it's better to move on this slide.
Yeah.
So all of the high order effect is suppressed by this factor, as you know. The variance of the density field. I mean, okay, I will explain this slide, then answer your question. what's the lessons we can learn from this toy model, simple toy model? The point is we are working in a perturbative regime, and in this perturbative regime, the expansion parameter is this variance of the matter density field. And here I'm showing this scaling of this parameter as a function of scale. I mean k versus this delta squared. And here's 0.1, k of 0.1. And at this scale, this delta square is just 0.1 or something like that. So perturbation theory should work. And this is the expansion parameter. So all the higher order effect kind of loops or higher order correlation functions are suppressed by this factor. This factor squared or 2/4 or something like that. And the point is, in some cases, the power spectrum analysis becomes suboptimal. In this case, we have some degenerate parameter in the degenerate parameters in the power spectrum analysis. But if the bispectrum has different dependence on that parameter, adding bispectrum recovers the full field level result. And another point I'd like to make here is, so this model, this is quite simple toy model, but still this quadratic term produces all the endpoint function. I mean, this produces a trispectrum, 5-point function, etc. But the point is, all these higher order endpoint function is kind of useless to get improved constraint on cosmological parameter. So information encoded in the bispectrum and the power spectrum is almost optimal or sufficient to get cosmological parameter. And to answer your question, so what? Well, I can write something on the blackboard. Sorry, but where is the? I think, you know, P linear plus, how can I, okay. P is just P linear plus, one loop is just P linear squared, right? Bispectrum is this leading order 3-level bispectrum P linear squared plus blah, blah, blah. But covariance of P, leading order covariance is kind of P linear squared. Yes. Thanks. But covariance of V is P linear, just cubed. Then if you take ratio, so signal P over by kind of P signal and P noise, P noise is, so leading order, of course, we have some usual P linear stuff, but plus this is suppressed by, okay, this is squared, I mean. This is suppressed by another factor of P linear, so this is P to force. So what I mean, the signal to noise of the one power spectrum is this guy, but as you know, bispectrum signal noise, if you compute this, then we have just a P linear force versus P cubed, then this is just P linear. So this should be P linear, I think, or P to 2. So this signal to noise is greater than the one loop. Is it clear now?
Yeah.
You should know it. Anyway. Okay. So we didn't find any evidence that there is additional information beyond the bispectrum with this toy model. Yes. But one might say, like Teppei pointed out, okay, this is just toy model. It's quite far from the reality. And we did kind of all the tests, including all the kind of reality stuff. But I think that there are only two stuff we should consider compared to the previous toy model. One thing is, of course, we should include the correct gravitational evolution, or we have to kind of displace the particles in correct way. The other stuff is we also have to add a bunch of higher order galaxy bias. And due to the time limit, I skipped all the details. but the upshot is this. So we included all the reality. I included the correct displacement as well as a second order galaxy bias, which is kind of sufficient to describe this scale. And here's the result. Now, this red one is a result from the power spectrum plus bispectrum. And blue one is a field level. And you can just focus on this plane. This is a plane for the power spectrum, cosmological parameters. And of course, the agreement is not so good as in the previous result. But again, the point is the error bars looks quite similar. Actually, if you look at the numbers or values, that's kind of 10% difference. But this is acceptable. So the point is neither this correct gravitational evolution nor this higher order galaxy bias doesn't change the result. Again, even for the realistic case, the trispectrum or any other higher order stuff is kind of useless. So this is a summary. So there's kind of so-called field level inference, which is optimal method to analyze the non-Gaussian cosmological data. And people hope to use this to get much more information compared to the power spectrum and bispectrum. But what we found is, as long as you are working in the perturbative regime, there's always some hierarchy controlled by this expansion parameter. And the takeaway is for galaxy clustering and in perturbative regime, full field level inference is almost equivalent to the power spectrum plus bispectrum. And I hope I could convince you guys that you don't have to work on the field level stuff. And that's it. Thank you.
So your last most realistic one.
Mm-hmm.
So if you overplot the constraint only from power spectrum.
Okay. This is for the real space. So in real space, you cannot kind of select degeneracy between A and B1. It's the same as kind of this plot. But actually, let me check if I have that plot. No. But I can show you, probably you are interested in the RSD stuff. And probably this.
I'm more curious if you if P plus B gives a similar level of field level, maybe if you add trispectrum, it might be better than field level.
No. Why?
If you have improvement by adding bispectrum is significant, you can expect some improvement by having trispectrum.
No, okay, I can say something about that. So here's a signal to noise. Again, this blue line is corresponding to P, and orange is bispectrum.
I understand that. That's why I want to see the result only from power spectrum.
Well, again, in real space, adding bispectrum drastically changes the situation because, okay, let's move on to back to this simple stuff. Okay. The only hope to select degeneracy between B1 and A in the power spectrum lies in this term. And as I answered to Stephen's question, this effect is subtle compared to this leading order bispectrum. This means, of course, you're correct, trispectrum has another dependence on B1 and A, but this effect is subtle compared to the leading order bispectrum. So again, there's some hierarchy. Yeah.
Okay, so if you did an intermediate step, so since you have an intermediate initial condition realization that gives you the final observed data,
Right?
if you just measure the power spectrum of that.
Mm-hmm. You mean initial condition, you mean? Power spectrum initial condition.
Yeah,
Okay.
I like to call this, the loose people, they would call it a reconstructed initial condition.
Okay.
Different people have different
Okay.
but just the initial condition.
Mm-hmm.
If you now just measure the power spectrum of the initial conditions, which is almost Gaussian because it's constraint realization,
Sure.
then you don't need the bispectrum. Is that correct? Then you have zero information because it's almost Gaussian.
I think that's correct. Yeah, in the level of the initial condition, there is no degeneracy in B1 and etc. So if you focus on the cosmological parameter, yes.
So in some, because the intermediate.
But I think this reconstruction involves higher order correlation function.
Well, the reconstruction is a highly complicated process.
Right.
But there is still a simplification that instead of having to collapse, instead of having to do a full field level, like huge dimensional description of the data, you're still left with only one power spectrum, which is the one variable. So you still have vastly compressed the data. And so there's an intermediate step where you get the fast data compression that is intermediate between having the
I agree. If reconstruction is
functions versus the all.
Yep, I think that's another way. Yeah, if reconstruction is first. Yeah.
But you're doing it anyways. I mean, if you're doing it, you might as well measure it.
I think there's a chicken and an egg problem, right? Because you're assuming you can do reconstruction assuming you know what the nonlinearities are, but he's solving for what the nonlinearities are.
Right.
So he's doing the inference.
Yeah, inverse model or forward model stuff.
I realize that. No. What I'm just saying is, you make it sound like as if there are only two possibilities. I use P plus B plus perhaps even more or not. Or you do a full field level. I'm just saying in the full field level, even in the full field level, there is an intermediate step, which is a power spectrum of your initial power spectrum, which is a much smaller space. I mean, it's a way of compressing your field level. In other words, you can compress the information in your field level reconstruction to a single initial power spectrum. So that's still a simplification.
I suppose one way is you could construct some approximate reconstruction that kills all the non-Gaussianity.
Yes.
I guess if
Yeah.
you can model that process in addition to this.
Right.
That's what I don't know if you're familiar with our papers. Of course, we've been promoting that what's it called? The barotropic reconstruction achieves 90% of that at almost no cost.
Well, if it's no cost, yeah, we should use it. Yeah. Okay.
And the barotropic. I'd love to compare the comparison of this information with barotropic.
Okay. Well, but my upshot is we don't have to work on this full field level. So yeah.
You don't even need a bispectrum. You can skip this. You just skip
Wow.
everything.
Well, but bispectrum is not so computationally expensive.
But
So
it's much more expensive than barotropic
okay.
mapping.
Sorry, I have one question.
Yes.
So for the mean result, where the information is or constraining power coming from?
First of all, I would like to say it's their responsibility to explain that. And
I asked the same question.
what's the answer? I'm curious about that.
We'll turn on the
Anyway, I can say about the differences between our stuff and their stuff. The overall framework are kind of the same, but the difference, there are several differences. So first of all, in their analysis, they use a so-called SPI, simulation-based inference, for the P plus B. So what they did is run some simulator, measure the power spectrum, bispectrum, and construct a kind of emulator for that. In our case, we compute the P plus B in analytical classic way. We don't rely on the simulations. And another stuff might be the data they used. So we did a kind of apple-to-apple comparison. That means we use the same forward model in the mock and the inference. But they use n-body Harrow as a data, mock data. But on the other hand, the inference, they are using perturbation theory. So in principle, they can be different. But at this point, I would like to say information should be in the signal or model, not the data. I mean, okay, think of the Fisher matrix.
Yeah.
So Fisher matrix doesn't care about data. So there are kind of difference in the data, but I think that doesn't make any difference. And the third point that I noticed is I included up to quadratic order by galaxy bias, but they included up to cubic order.
I see.
But if you add cubic order bias, then you get this result, then I'm sure there's something wrong.
I see.
I can personally tell you our guess what's going on, but I think this is recording, so I cannot.
For the P plus B and field level, how do you implement the same K max? And do you
Well, it's easy.
do the
I mean,
same thing?
I mean, in this, wait. So we can just write down the likelihood and summing over the signal and data up to this k max in the likelihood. This is the kind of usual stuff in the P plus B. And the same thing can be done. I mean, we have a bunch of Fourier mode, but we can, of course, know the amplitude or magnitude of this Fourier mode. And we can just pick up the density field up to this k max to sum up.
So the generative steps you already generate only up to the k.
No. In generation, actually, okay. Well, I think I now understand your question. I mean, there is kind of two cutoff in this process. Yeah, probably it's. So here, I'm generating some random field from the initial power spectrum. And of course, at this point, I have to introduce some cutoff. This is kind of implicit cutoff, and I take this implicit cutoff much greater than the likelihood in here. Kind of factor of 2 or something like that. Roughly speaking, this k max is 0.1, but I'm sampling the initial condition up to 0.2 or something like that.
Just wondering if different implementation of k max can potentially explain.
Well, I mean, what we found is, yes, I'm sampling the initial condition up to some larger scale compared to the k max in likelihood. But then, if you, for example, here, I have also samples from the initial conditions that I can kind of compare this sampled initial condition with a true input value. And for example, you can compute a cross correlation coefficient from reconstructed initial condition with a true input. And what I found is, although I sampled initial condition up to larger k max, but reconstructed, I can successfully reconstruct the initial condition up to k max, not the cutoff in the initial condition. So this means I'm sampling some, garbage. Above k max, I'm just sampling from the prior. So they have no information. They don't have any information about that. Information lies in here, right? Probably it's better to write. So if I compute the cross correlation coefficient, which is defined like delta reconstruct versus kind of truth, divided by some normalization, then if I reconstruct the initial condition successfully, then I would get some 1. And there's again 2 cutoff. One is k max in the likelihood. The other is kind of lambda in the initial condition sampling. But the point is, I'm comparing the prediction with data up to this scale. So the cross correlation coefficient drops around this scale suddenly. So this goes to 0. So this means the mode between this k max and lambda are sampled from the just prior, not conditioned to the likelihood. So this means there's no kind of cosmological information. Any other?
Well, I think it's exactly 3:20.
Okay,
So,
nice.
Well, if there's no further question, let's thank him again.